Want me to say out loud? You want to come up? So yesterday we talked about pressure was where we stopped. Pressure is equal to force divided by area. So in terms of gases, what pressure is, and I'll draw a picture. So if you were to blow into your hand, you'll feel an increase of pressure. Or if you have a can of CO2 gas, so a can of gas or something, or you should know your Coke can is under a lot of pressure. What pressure is in terms of gases is we have these particles all moving around randomly. These gas molecules are always moving around. There are some times one will be moving in this direction, the other moving another. They'll occasionally collide in with something. Either it's, yeah. So they'll constantly run into each other and they'll bounce around. Think of like pool or billiard balls. But because there are so many particles, they're obviously going to occasionally run into the wall. So imagine like taking a baseball and throwing it on something. You feel a force when it hits you, right? So you could think of it as lots of baseballs being thrown around. The pressure that you feel will be the billion particles that randomly occasionally hit the sides of the wall and bounce off. So one will come in, hit the wall, bounce off, and this bouncing feeling is the force on the wall. So again, the equation for pressure is the total force divided by the total area. So the force of all those impacts divided by the surface area is going to be equal to the pressure you feel. At standard sea level, so if you were on the coast, on the beach, we use standard pressure of 1 atmosphere. So I told you I'll write down STP, stands for standard temperature and pressure. The standard temperature is 0 degrees Celsius. Standard pressure is going to be 1 atmosphere. That's about what we have here, 1 atmosphere of pressure. In chemistry, we will use quite a bit of different pressure units. If you ever go to the doctor and get your blood pressure taken, they measure it in millimeters of mercury. Most science and physics use something called Pascal. Pascal is very, very small, so we usually do kilopascal. By the way, 101.325 kilopascals is equal to 1001,325 Pascal. But usually we will write it and use kilopascals over normal pascals. And by the way, all three of these are equal. So 1 atmosphere is equal to 760 millimeters of mercury. So there's a conversion factor between atmospheres and millimeters of mercury. 1 atmosphere is also equal to 101.325 kilopascals. So that's another conversion factor. Or we can convert between millimeters of mercury and kilopascals, because 760 millimeters of mercury is equal to 101.325 kilopascal. So that's another conversion factor. So writing that all out for you guys. We can use the constants 1 atmosphere to 760 millimeters mercury, or 1 atmosphere to 101.325 kilopascals, or 760 millimeters mercury to 101.325 kilopascal, or the inverses. So you can flip this around, mmHg to 1 atmosphere, and so on and so on. So these are the conversion factors. 1 atmosphere is equal to this. So if you need to convert, you can plug in these to the grid. So 1 atmosphere is equal to 760 millimeters mercury, which is equal to 101.325 kilopascals. That relates all 3 units. And if you're wondering what millimeters of mercury is, so if we were to take and fill a bucket, so if we were to fill a container full of mercury, and then if we were to take a tube and also fill this up with mercury, so we have mercury inside here. What would happen is that the mercury inside the tube is going to drop down by some amount, so it's going to move downward. And the difference, and let me look it up a picture. See if it's better explained. It's better. Would have been better. That was one way of doing it. What normally is done, let me open it up. Is that we have one way of doing it is a U shape. So right here is a vacuum. This would be completely filled with mercury. You turn it over so that we have some pressure here. So 1 atmosphere. And then we have a vacuum, so this is completely empty, no air inside of it. And this would be, the right side would be more likely. So air is going to push this mercury down. Gravity is going to pull the mercury down. The difference between gravity pulling this mercury down and air pressure pushing this mercury down, you're going to get some height difference. If you measure this height difference, it will correlate as linear to the pressure on the side of the tube. Does that make sense? Let me redraw it. Using a U shape. U shape is better. Don't specifically need to know this. So we have this completely sealed. So if you were to put mercury into this side, what's going to happen is if you turn the U shape up, gravity is going to make this fall. And I do it like this. Gravity is going to pull this down. So you would expect something like this. You'd expect it to even out if you had a U shape of liquid inside there, right? Now, if this is a vacuum, meaning there's nothing in here, and this was open to air, the tiny little air molecules are going to keep bombarding the end of the mercury. It's going to be pushing it down. So we have gravity. Gravity is pulling this down, and it's pulling it down over here. But we also have air pressure pushing down on the end of the mercury. So what ends up happening, again, if this side is sealed off and this side is open, what we end up having is that the air is going to push this down, and the mercury is going to do this. If we measure the height between here and here in millimeters, so in millimeters of, and if we use our liquid mercury, then if this was an atmosphere, meaning that this was up in this room, then we would measure a distance of 760 millimeters. That in inches is 29 inches. So that's equal to 76 centimeters, or 0.76 meters, or 29.9213 inches. So 76. So we would measure the difference between the top and bottom. It'd be a very large, U shape, but it would be that height. You could also do it with water, but water is about 30 feet. So you would need to go up to the top of a building to do it with a long hose. But you could measure pressure using water or any deal. But mercury is small enough that we can do it using this mercury. I think that's right. I might be slightly wrong. It might be half this. Let me see, because looking at the image, that might be slightly wrong, because I'm fairly sure the original experiment had a inverted tube and then a pool of water, so that you have mercury, and the mercury comes up like this. I want to say this is the original definition, and then you calculate this distance, and that distance would be 760 centimeters. I want to say it's a different math, but at least you are somewhat getting the idea of what a millimeter's mercury is. You don't really need to know exactly how it's measured and how it came about. All you need to know is a unit measuring pressure. So, why does air pressure decrease as you climb a mountain or ascend in an airplane? One way of wording it. So what's another way of saying they're more spread apart? Using chemistry, what's that curve? Less dense. So as you move upward through the atmosphere, the density of the air decreases, or they get more spread apart. Yes. No, it's because keep your mask on. Gravity is trying to. I'll draw a picture. Yes. All right. So imagine you're trying to fill up a container with marbles, and the marbles always constantly move. So remember our assumptions under kinetic molecular theory. We assume that regardless, the air molecules are in constant motion. They never stop. So gravity is going to want to kind of pull these down. So it's moving in some random direction, but gravity is going to pull them down. When it gets to the bottom, it's going to hit the bottom, and then it's going to bounce back upward. Think of a basketball. So gravity is going to constantly be trying to pull these back down to the ground. So the more the particles are going to come hit. So imagine what would happen if you take a basketball and you throw another basketball at it. It's going to hit the basketball, and then it's going to bounce back up. Now imagine, again, some more particles coming down. So gravity's trying to pull them all down. If they weren't constantly moving, if they could stop moving, then what would happen is all the air in the world would just sit on the surface. Almost like a liquid. We'd assume that all the air would be tightly packed onto the ground. But air molecules are constantly moving. When an air molecule comes and hits one, it's going to bounce back upward. And so we're going to get as we come up, they're going to be constantly bouncing and coming back up. Gravity is going to pull some more air molecules down. They'll come in, hit, then bounce back up. And what happens is the ones at the top are more able to move around, and so they're going to constantly be hitting and bouncing back up. Whereas gravity is going to keep these down here, but occasionally they're going to bounce and then move all the way back up. Gravity wants all the air on the surface. But since they're constantly hitting and bouncing, they'll bounce back upward. And then gravity would pull them back down to the ground. But when they come back down, because of gravity, they're going to end up hitting another air molecule and bouncing back upward. And then gravity is going to try pulling them back down. So what we see is gravity will keep most of them down closer, but they're still going to keep bouncing up. We'll occasionally have one at the bottom hit and keep bouncing all the way back up. And that is the reason why it's more air molecules at the bottom. If they weren't in constant motion, they would all be at the very bottom. Almost like a liquid of air on the bottom. But since they're constantly in motion, they're going to constantly be hitting, colliding, and bouncing back upward. They can't just sit still. So as the density decreases, there are fewer molecules colliding with the surface, hence less pressure. So STP, standard temperature and pressure. It's 273.15 Kelvin, and the pressure is 1 atmosphere. And if I go too fast, I'm going to go back. At STP, regardless of what chemical you're measuring, one volume of 1 mole of gas is 22.4 liters. So if you had 1 mole of a gas, 6.022 times 10 to the 23 particles or molecules of a gas, it would occupy a volume of 22.4 liters if your temperature was 0 degrees Celsius and your pressure was 1 atmosphere. So at 1 atmosphere, 0 degrees Celsius, the volume is 22.4 liters. So number of molecules is 6.022 times 10 to the 23. And now we have a way of converting between volume, pressure, and temperature, assuming that finding the volume of a gas. If we knew that the pressure was 1 atmosphere and the temperature was 0 degrees Celsius, it's going to have that volume. We'll go later and figure this out. So phase and state changes, we'll do this later. Go switch to another PowerPoint. I will come back to this PowerPoint after I go over the gas laws. Give me a second. I have to look up. I have like a lot of PowerPoints saying gas laws. See if I can preview. I know which one it looks like. So it's all caps. Alright, so a little review. Kinetic molecular theory. Particles in an ideal gas. We assume that the particles are so small they have no size. They're just individual points. When they collide, it's elastic, meaning they'll just bounce off of each other. There's no attraction to them. And they're in constant random straight line motion. They don't attract or repel each other. And the average kinetic energy directly relates to Kelvin temperature. So the average kinetic energy, the average motion of all of them, is equivalent to the temperature. Make sense? So a little review. So some characteristics of gases. Gases expand to fill any container. Random motion, no attraction at all. Gases are fluids. By the way, if you did not know this, a gas is a fluid. What's the definition of a fluid? Something that flows. So if I say your movement was very fluid, I'm saying your movement flows well together. It's not like all choppy. I'm saying it just flows together. So air flows. You can obviously blow or wind blows. Gases are considered fluids. So all gases and liquids are fluids. There's no attraction between them. Gases have very low density. So because they have no volume, there's lots of empty space. And here's an example of solid, liquid, and gases. Again, we assume those little tiny circles are really, really small. Gases can be compressed, so there's lots of empty space. Gases undergo diffusion and effusion. What this means is, like for example, your mask. When you breathe out, CO2 can diffuse through the small pores of your mask. It means it just can go through porous materials. Fusion is similar, except for it's more of a solid. It can go into, or for example, if you have pure water just sitting here and you start breathing into it, you can actually have CO2 go into the gas. You can put CO2 into a liquid like water, or carbonate your Coke. So you can compress gases. Also, if you open up a perfume, the gas particles can escape. Always use absolute temperature. Kelvin is an absolute temperature scale when working with gases. If you don't know how to convert between Celsius and Fahrenheit, that's the equation. So to convert from Fahrenheit to Celsius, you subtract 32 from the degrees Fahrenheit and multiply it by 5/9. And again, you do 273.15. And yeah, you could add in. So to convert between Fahrenheit to Kelvin, you just add 273.15 to the equation on the left. So absolute 0 in Kelvin is 0. That's where it starts. In Celsius, it's negative 273.15. In Fahrenheit, it's negative 459. About. Water freezes at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit, or 100 in Celsius, or 373.15 in Kelvin. So pressure is equal to force divided by area. Which do you think exerts the most pressure? A high heels, because there's less area. Does anyone know what the shoes on the right are called? Snowshoes. So they increase the surface area, which means you can walk on your. It's because you're increasing the surface area. The area on the bottom is getting bigger, so the bottom number is getting bigger. The force is staying the same, so your pressure goes down, allowing you to walk on snow without compressing it. Here's the picture I was looking for. So this is a barometer, a mercury one. So you have a very long column. Again, there's no air in the top. It's literally empty. It's a vacuum, like outer space. And you can measure the difference between the top versus, so again, gravity is pulling down on that column. So gravity wants to pull it all down. But atmospheric pressure is pushing it up the tube. And if you measure the difference between them, that gives you, if you do it in millimeters, you'll get millimeters of mercury. This is where millimeters of mercury comes from. And it's called a barometer. And then we have this one is a U-shaped, a U-tube manometer. I forget how to pronounce that. Manometer. I think it's a manometer. That is one way of doing this. The difference, though, is between this one is you have a gas sample on the left and you have atmospheric pressure on the right. So when using this, you're going to only find the difference between atmosphere and the gas, whichever one pushes more stronger. So we have kilopascal. All these are equal. By the way, you might see torr too. Torr and millimeter mercury are the same thing. They just renamed millimeters mercury to torr. We also have PSI, which is pounds per square inch. That's probably how you measure the tire pressure in your car, is in pounds per square inch. 1 atmosphere is equal to 14.7 pounds per square inch. By the way, how much pounds of pressure do you think is on your body right now? So every inch of your body there is 14.7 pounds of pressure on it. Every inch. You estimate your body has, let me actually look that up. Surface area of a human. So for the average adult male, it's 1.99 cubic or square meters. So inches square. That is about 2950. So 2945 times 14.7. That is about 43,300 pounds of pressure on the surface of your body. Why aren't you instantly crushed? I mean, it's still 14. Why can't you feel? So y'all know what 14 pounds weighs? About 20 pounds, maybe. Y'all know the 20-pound weight. Why don't you feel like a 20-pound weight? Multiple of them all on your arm. Every inch of your arm. Now imagine every inch there's a 20-pound weight or a 15-pound weight. Your body is counteracting it. So if you press your two hands together, they don't move. Because the pressure or force from this hand and the force from this hand cancel each other out. Your body exerts a lot of internal pressure. And the two pressures, I mean, of course, you can feel your skin being pinched between them. But the pressures cancel each other out. Yes. Otherwise it cancel, or otherwise it would be moving. If you have two unbalanced forces, like this one pushes with a stronger force, then you cause movement. By the way, the units of kilopascal and the reason why we use it in science is newtons per meter squared. I'm probably not going to be able to do a lab tomorrow. Maybe I'll finish all this up. I don't know yet if I'm doing a lab tomorrow. But just going back over this. Do come prepared tomorrow for a lab in case I do set it up. Meaning, yes. Who's going? Then we won't do a meeting. We won't do a lab tomorrow. I'll just review some stuff. Because it's a really fun lab. I'm pulling out the vacuum saber. Alright, sounds like a plan. So standard temperature is 0 degrees Celsius, 1 atmosphere. So here is the main topic. This is what we're going through. This is the main topic of this unit. The gas laws. We have Boyle's law, Charles's law, and Gay-Lussac's law. What is Boyle's law? So look at just volume and pressure. What do you notice? If we multiply the pressure with the volume, what does it equal? I mean, there is some little differences, but it's basically constant. If you take the pressure and the volume of a system and you keep the temperature the same, it stays constant, the product of pressure and volume. So Boyle's law is pressure times volume is equal to some constant. Pressure times volume is equal to some constant. Because C stands for the speed of light. Constants are usually K's. We can use occasionally a C, but usually we use K. So, In other words, the pressure and volume of a gas are inversely related if we have constant mass and temperature. So we keep the mass the same and we keep the temperature the same. As pressure goes up, volume goes down. As volume increases, so look at volume, as the volume is going to increasing to the right, pressure is decreasing. Alright, Charles noticed something about volume and temperature. He was looking at volume and he was looking at temperature, and he noticed the relationship. If we took volume and divide it by temperature, it equals a constant. So volume divided by temperature is equal to a constant. In other words, the volume and absolute temperature, note this is not delta T, this is actual temperature and absolute temperature, has been Kelvin, are directly related. So if you increase the temperature of something, the volume is going to have to increase in order to keep it at constant mass and pressure. So this only concerns itself if pressure is kept constant. So for example, if you were to blow into a balloon, or let's say a hot air balloon, as the gas inside the hot air balloon is heated, the volume of the balloon has to increase because it's still at atmospheric pressure. The inside of the balloon has to stay at 1 atmosphere because it's up and at one end, and obviously 1 atmosphere is the standard pressure. Yes. So as you increase the temperature of a gas, if the pressure stays the same and if you're not losing any mass, then the volume is going to increase. And Gay Lussac, he discovered a relationship about temperature and pressure. It's interesting that 3 different people came up with 3 different properties, and not just one person come up with all 3. You would think once you discover a relationship between pressure and temperature, you might want to check about volume and temperature, or volume and pressure, but not how. I'm not for sure. So he noticed that a relationship between pressure and temperature. If you take pressure, and again this is absolute temperature, so Kelvin, and you divide it by, this is the reason why you can't use Celsius, because it's because at standard temperature, we measure everything. If we measure everything at standard temperature at 0 degrees Celsius, you'd be dividing by 0. You can't divide by 0. Hence the reason why you need to use Kelvin. But you notice that pressure and temperature is equal to some constant K. So the pressure and absolute temperature of a gas are directly related. So imagine that you were to put a Coke can on top of a fire. There's a little bit of gas in there, right? At the top of it is not 100% liquid. But you'd be heating up that small amount of gas. The volume is staying constant, but what happens? Pressure increases. And so the pressure is going to increase until the can bursts and no longer hold that pressure. So now we have a combined gas law. So we know that pressure times volume is equal to some constant. We know that volume divided by temperature is equal to some constant. And we know that pressure times some temperature is equal to some constant. And so we have pressure times volume over T is equal to some constant. I'll illustrate that. Yes, thank you. I'll go ahead and do it. So the code word is on the screen. There's the code word. Go ahead and type it. So we have that pressure times volume is equal to some constant. I'll temporarily let it be equal to A, or K1. I think y'all are smart enough. Pressure times volume is equal to some constant K1. We know that pressure divided by temperature is equal to some constant K2. And we know that volume divided by temperature is equal to some constant K3. So if I combine all three of these, pressure times volume is equal to some constant. Pressure divided by temperature is equal to some constant. And volume divided by temperature is equal to some constant. Note these are all different constants. Combining all these together, this would be equal to some combination of these constants. And so we can set it equal to a new constant here. Because if we change volume but keep pressure the same, volume divided by temperature is equal to some constant, so it's going to stay constant. So, what this means is that if you're at some initial pressure, some initial volume, and some initial temperature, at some later point in time, so that stays a constant. So if you're at some initial pressure, some initial volume, and some initial temperature, it's constant. That factor P times V divided by T never changes. It stays constant. Which means at some later time, your final pressure times your final volume divided by final temperature has to be the same as your initial values. Right? One way of rewriting it is this. I do not recommend you write that equation. That's just a neat way of doing it all on by itself. Oh, were y'all even able to see that PowerPoint? Okay, so it goes over this. So if we have so we know that PV divided by T is equal to some constant. So that means that your initial, this is initial pressure, times initial volume divided by initial temperature has to equal K. And K also has to equal your final pressure times your final volume divided by your final temperature. So they're both equal to the same constant. So we can set them equal to each other. I recommend you memorizing it like this. It might be easier to work it out. P1, so multiplying T1 to this side and multiplying T2 to this side. So multiplying both sides by T1, T2. The T2 and the T2 over here cancel each other out. The T1 and the T1 cancel each other out. So we get P1, V1, T2 equal P2, V2, T1. Oh, by the way, this class uses algebra. I assume you know algebra. I am not an algebra teacher, so I don't teach it. But this class will use algebra. So this is one way. It removes all the fractions. I recommend not using it. If we instead look at this equation, P1 V1 over T1 equal P2 V2 over T2. Yes, the algebra is going to be slightly harder with this version of the equation. but you have all your initial values on the left and all your final variables on the right. I have seen that if students use this problem, this format, they'll occasionally do this. P1, V1, T1 is equal to P2, V2, T2. That is wrong. You're supposed to have T2 here and T1 here. So they'll occasionally get it wrong. This version of the equation is the one I recommend so that you have all the initial values on the left, all the final on the right. It doesn't matter if you do want to use this. Just know that your temperature on the left is going to be final. It might be help you with the algebra to do that. So let's work over some examples. For tomorrow, I'm just going to pass out notes. I forgot to print them out this morning. And I'll go over some more examples tomorrow. That's what I'll do. And I'll set up lab Thursday. You can always go back and watch the video if you're at that. So a gas occupies 473 cubic centimeters at 36 degrees Celsius. Find its volume at 94 degrees Celsius. So just remember the combined gas law. P1, V1, temperature 1 is equal to final pressure, final volume over T2. So just remember this equation. Let me actually go in. Well, this is what we're going to be doing tomorrow.